All right, hey guys, wanted to work you through that last free response question. All right, so let me share my screen with you and show you guys how to tackle a question that looks like this. All right, so last one in the packet, scroll all the way down. All right, it says a sample of C2H4 is placed in a previously evacuated rigid 2-liter container, and we heat it up from 300 to 450. The pressure of the sample, all right, is measured and plotted below. So if you take a look, temperature down there on the x-axis, pressure on the y, looks like as the temp goes up, the pressure goes up. Shouldn't be a surprise, right? We've talked about that before. Right, that's a graph representation of Gay-Lussac's law, and we would understand that at the molecular level as well. And that's what number A, or rather letter A, is saying. It says describe 2 reasons why the pressure changes as the temperature increases. You have to say what happens to the molecules, the molecular level. All right, so the first one is pretty easy, okay? Everyone always understands, oh, temp goes up, molecules have more energy, right? They collide more frequently. So there's one reason the pressure goes up. The increased speed of the molecules makes them collide more often. The second one, right, is a little more subtle, all right? If you're colliding, right, with a higher velocity, you're also colliding with more force. And remember, pressure is the number of collisions and how hard they're colliding. So the second factor that would be increasing there would be the force of the collision. All right, so the 2 reasons why the pressure changes as it goes up is the increased temp makes the molecules collide with more force and collide more often. All right. Then we kind of transition into some other stuff. It says C2H4 reacts readily with the HCl, and we make the C2H5, and then they give us the reaction. They throw a delta H in there, all right? Remember, negative delta H means exothermic, all right? And that tells us some things, all right? So with an exothermic reaction, we know that the bonds being formed in the products must be stronger than the bonds being broken in the reactants. We know that it would warm up most likely because you're giving off that excess energy. All right. We know that the products, right, have a lower potential energy than the reactants. The bonds are stronger, and that makes the potential energy lower, so you release that excess. I don't know if we'll need it, just telling you what the delta H means. All right, B says when the HCl is injected into the container, the total pressure increases. Then as the reaction proceeds, the total pressure decreases. Explain the decrease in total pressure in terms of what happens at the molecular level. So when I first inject the HCl, the pressure jumps. No big surprise. I'm injecting a gas. I inject new particles. They're going to collide more. But then as the reaction runs, I get less and less and less collisions. Right? So the temperature didn't change, so they're not going slower or colliding less forcefully. So the only reason the pressure would decrease is that somehow we had less particles in there. And the reason we're getting less particles is because of the reaction. We are taking 2 gases, it's C2H4 and the HCl. When they react, they turn into 1 gas. So you have 2 separate particles bouncing and colliding. When they hit each other, they bond. Now you have 1 particle that can't collide as often. So for letter B, you would want to say something like the decrease in pressure occurs because you have 2 moles of a gas becoming 1 mole of a gas. This will decrease the number of particles and collisions, therefore lowering the pressure. Right. On to the bottom one. Right. This is linked to this chapter. Right. It's saying proposed formation is the 2-step reaction mechanism. So this is one of those elementary steps. Notice fast steps. Rate determining step is another way of saying slow step. With these guys, watch out if you see fast reversible equilibrium, right? Because remember, we can solve the fast reversible equilibrium for one of the things in the slow step and plug it in. We're not seeing that here, just making sure you're looking for it. C says, write the rate law for the reaction that's consistent with the mechanism above. So remember, the rate law from a reaction mechanism is the only time you can use the coefficients as the exponents. Right? So the rate determining step, the slow step, is the one we focus on. So it's going to be rate equals always K, don't forget the K, reactants to some power. And you have two reactants in that first step, C2H4 and HCl. Those both have coefficients of 1, and in the slow step of a reaction mechanism, you can use the coefficients as your exponent. You don't need to write the ones. I just wanted you to see that it matched the coefficients. D says, identify an intermediate in the reaction mechanism above. Remember, an intermediate is a substance that shows up on the right first. It gets produced, then it gets consumed in a later step. So it has to be on the right side of an equation first, then the left side second, and it can't be around in the overall reaction when we're said and done. Right? So there's two of them in this. The C2H5 plus shows up on the right of step 1, and then it's on the left of step 2, and they'll cancel. The Cl negative is on the right of step 1 and the left of step 2. They will cancel, which makes them intermediates. If you see the reverse, it's on the left first, then the right second, that would be a catalyst. All right, so intermediates, they're on the right first, then the left second, and then they cancel. If it's on the left first, then the right second, it is a catalyst, and again, it has to cancel. All right, last part of this question here. It says, using the axes provided, draw a curve that shows the energy changes that occur during the process of the reaction. It should illustrate the two-step mechanism and the enthalpy change. So if I'm going to draw this guy, remember, in these potential energy versus progress ones, you have the same number of hills as you do steps. So you look up, it's a two-step mechanism. So I know I've got 2 hills. The highest hill, the biggest activation energy, has to come from the slow step. All right, so the first step has to be the bigger hill. So I'm here, I'm going to go up. There's my slow step, biggest activation energy. Then I get another one, another step, right? So the biggest activation energy is in step 1. The activation energy in step 2 is not as high. Right, now, to decide where the graph finishes, we need to know if it's endo or exo. If it's endothermic, it stays above the reactants. If it's exo, it goes below. Earlier on, I said that it was negative 72.6 kilojoules per mole, which means we finish this guy down here. So the delta H for this guy is negative 72.6. That's the distance from here to here. They didn't give us the activation energy barrier, so that would be up high. Last but not least, it said on the diagram above, clearly indicate the activation energy for the rate determining step. I already did that just instinctually. Remember, it's the distance from the reactants to the activated complex. So it would be this distance right here. All right, hope this helps you guys out. Feel free to message if you have any questions.